Welcome back, everyone. Ready for another deep dive? Today we're tackling a research paper you all chose, Theoretical Limitations of Multi-Layer Transformers. Sounds intimidating, I know. But stick with us, it's fascinating. We're basically trying to understand the limits of what these large language models like, say, ChatGPT can really do.
Yeah, this paper is like kind of a big deal because it lays out the first hard limits, unconditional limits on multi-layer transformers. And it does it like without relying on assumptions that haven't been proven, which is, pretty huge.
One of the things that struck me right away was how the paper points out that, we've had a good grasp on single-layer transformers for a while now, but the multi-layer ones, the ones that are powering most of these LLMs we see today, they've been a black box until now.
Right. It's like we finally got a peek under the hood.
Hi.
And what they found looking at this sequential function composition.
Sequential function composition, that's a mouthful.
Yeah, so imagine a recipe, right? Each step builds on the one before it. You mess up early on, the whole thing's off.
Ah, I see. So the paper's saying that these small multi-layer transformers, the ones with, limited processing power, they struggle with these multi-step tasks.
Yeah, like when the recipe gets too long or complicated. And, this has big implications for how we design and use LLMs going forward.
Absolutely. The paper also dives into the whole depth versus width thing with transformers.
Yeah, turns out the number of layers, that's the depth, matters a lot. More layers, more horsepower to handle those complex tasks. Explains why some LLMs feel so much smarter.
Right, and it makes you wonder, like, what's going on inside those layers that makes such a difference? The paper also throws in a comparison of those encoder-based models, like BERT,
Good for understanding stuff.
and then the decoder-only models, like your friend ChatGPT.
Master text generators, those guys.
So does this mean, like if we go back to that recipe analogy, the encoder models are better at following those multi-step instructions?
They are. Turns out they can solve those tasks with way fewer layers, fewer resources than decoder-only models, like way more efficient. It's a pretty fascinating difference.
It really is. And, this ties into something we've been talking about a lot lately, chain of thought prompting, where you kind of guide ChatGPT to think step by step.
Totally. This paper kind of backs up why that works so well. Turns out chain of thought prompting can make a huge difference in how well a transformer handles these tricky problems. Like, it gives them more room to think, more steps to break things down.
That's such a good point. And for a long time, it seemed like progress in understanding these multi-layer transformers was stuck waiting on some big breakthroughs in computer science, like proving those circuit lower bound barriers.
Yeah, but this paper, it gets around that by focusing on how decoder-only models process information. It's a super clever approach and opens up some really exciting new paths for figuring these models out.
I'm glad you brought that up because the paper also talks about this historical shift, right? Like how LLMs went from being mostly encoder-based models, like that BERT we talked about,
Uh-huh, those are the early stars.
to now where it's almost all decoder-only models running the show.
Big change. And, in the beginning, those encoder-based models like BERT, they were awesome at understanding relationships between words. Like, they'd learn by predicting missing words in a sentence, getting that context down pat.
But they weren't as good at actually generating text.
Right.
Right. And that's where the decoder-only models like ChatGPT really shined.
Exactly. They're all about predicting the next word in a sequence, which is perfect for, writing, translating, all that good stuff. Plus, it's just more efficient for making text computationally.
And with everyone wanting these LLMs to create human quality text, it makes sense why decoder-only models became so popular.
Mm-hmm.
It's kind of cool how the architecture of these models has evolved to fit what we want them to do.
It is. But it wasn't just theory driving this. A lot of it was empirical, like trial and error, seeing what worked. There's a ton of research out there showing how different architectures perform, and decoder-only models, they kind of struggle with stuff like multi-step math problems or understanding logic arguments, things that need sequential composition.
And this paper, it gives us the theoretical why behind what researchers were already seeing in practice. It's like the theory catching up to what's happening in the real world.
For sure. And that brings us back to those layers again. The paper makes a big point about how the number of layers, that depth, is way more important than the size of each layer, the width, when it comes to reasoning and, putting things together, that composition.
So it's not just about making each layer bigger. It's about adding more layers to handle those tougher thought processes.
Exactly. Like if you're building a skyscraper, making the floors wider won't get you any taller. You got to add more floors.
Perfect analogy. And this paper gives us the theoretical reason why that holds true for LLMs too.
Yeah.
It's incredible how much insight they packed into this paper. It's like
Hmm.
we need to appreciate how big of a deal this research is before we even get into the nitty-gritty details.
Absolutely, because it goes beyond just saying, here's what multi-layer transformers can't do. It starts pointing towards solutions, like where do we go from here? How do we make them better?
It's like we're starting to understand the why behind the what, and that is so exciting.
Yeah, it's like we're cracking the code, finally. And that understanding is going to be so important for shaping how we use LLMs in the future, how they impact everything we do.
For some people, all this talk about sequential function composition, it might seem kind of abstract, head in the cloud stuff, but it actually has real-world consequences for how we use these LLMs.
Right. Like think about things that need step-by-step reasoning. Writing code with lots of interconnected functions or understanding legal documents with all their clauses and conditions.
Or even just figuring out a complicated recipe.
Yeah, exactly. And that's where these LLMs, especially those decoder-only models, start to hit a wall. They have to keep track of so much information, so many steps.
It's like you give them a puzzle, but they can only see one piece at a time.
And this research is telling us that's a fundamental limitation, at least for now. It's not that they're stupid, it's that the way they process information makes certain tasks really hard.
So it's about understanding what they're good at and where they need help. Like decoder-only models, they're rock stars at creative writing, conversation, translation. But for deep, multi-step reasoning, maybe not the best tool.
Totally. And knowing that helps us use them better, play to their strengths. Plus, it highlights how important it is to keep researching, keep pushing the boundaries. Who knows what breakthroughs are just around the corner? Maybe we'll have LLMs doing all sorts of crazy things we can't even imagine yet.
I love that optimism. And I think that's a great place to pause for now. We've covered a lot of ground, gotten a good feel for the big ideas in this paper, but there's so much more to unpack.
Yeah, we've only just scratched the surface. We haven't even touched on the autoregressive communication model they use to analyze these transformers. Or that really cool indistinguishable decomposition technique.
That's right. We've got plenty more to dig into. But for now, take a breather. Let all this sink in. And when we come back, we'll get into the nitty-gritty, the technical details that make this research so groundbreaking.
It's going to be fun. All right, so remember how we talked about that autoregressive communication model? The paper uses it to analyze multi-layer transformers, and it's pretty key to understanding where those limitations come from.
Can you give us a quick refresher on that? I'm still processing all the layers and stuff.
Sure, so it's like, picture those transformers as a bunch of players, right? Each one's holding a piece of information, but they can only communicate in a specific order, like passing a message down a line.
Like a game of telephone?
Exactly. And because of that, each player can only see the information from the players that came before them. That's what autoregressive means.
Gotcha. So that limited communication, that's what creates the bottleneck, right?
Right.
Makes it harder for the model to deal with those multi-step tasks, that sequential function composition.
Right. And to show how this bottleneck actually affects things, the researchers use this technique called, are you ready for it, indistinguishable decomposition.
Oh, yeah, you mentioned that earlier. It sounded kind of like a magic trick.
It kind of is. So they create these sets of inputs for the transformer that are basically designed to be like indistinguishable to certain parts of the model, even though they lead to different answers.
Okay, so it's like the transformers being tricked.
In a way, yeah. By showing that the model can't tell the difference between inputs that should lead to different outputs, they're proving that it doesn't have the capacity to keep track of all the info it needs to get the right answer.
So it's not just that the transformer made a mistake, it's like a fundamental limitation of how it works.
Right. And the reason for that limitation is, you guessed it, that information bottleneck we talked about, that autoregressive way the layers communicate.
Got it. That line of players passing the message down the line. But how do they actually show this limitation? Like, what do these indistinguishable inputs look like?
So they focus on two main properties of these sets. One is large remaining entropy. Basically, it means there's still a lot of variability within the set, even though they look the same to parts of the model.
Like, imagine a bag of marbles. You can't tell what color they are just by looking at the bag, but inside there's a whole mix of colors.
Perfect analogy. And the second property is large cover. That means these sets represent a wide range of possible answers for the task.
Okay, so it's not just a narrow set of possibilities.
Nope, it's broad. And by combining these two properties, large remaining entropy and large cover, the researchers show that there will always be some inputs in these sets that the transformer just can't handle.
So no matter how good the transformer is, it's bound to trip up on some of these inputs.
Exactly. It's a really clever way to demonstrate those limitations. And the paper doesn't just stop at explaining it, they actually provide mathematical proofs to back it all up.
So it's not just hand-waving, it's hardcore math, saying, this is how it is.
You got it. And the paper does a great job of explaining things clearly, using examples and analogies to help us non-math whizzes understand what's going on.
I appreciate that. We've been talking a lot about decoder-only transformers, because those are the stars of the show right now, like ChatGPT. But what about the encoder-only models, like BERT? Do they have these same limitations?
That's a great question, and the paper actually digs into that. It turns out there are some key differences between how these two types of models handle information, and those differences really matter when it comes to sequential function composition.
Okay, so remind me again, what's the main difference between those architectures?
So remember our game of telephone, that's like a decoder-only model. The message goes one way only. But an encoder-only model, it's more like a group discussion. Everyone can hear everyone else, past and present.
Ah, so more free-flowing communication, that makes sense.
Yeah, and that difference in how they communicate has a big impact on their ability to handle those multi-step tasks.
I'm guessing the encoder models, with their two-way communication, have an easier time.
You got it. Turns out they can solve those tasks using way fewer layers and resources compared to decoder-only models, like way more efficient. The paper even gives a specific example where an encoder-only model nails a task using a fraction of the layers a decoder-only model needs.
So if you need to handle a bunch of steps, an encoder model might be the better choice.
Could be. It really depends on the task. It's like you wouldn't use a sports car to haul a bunch of lumber, right? You'd pick a truck, the right tool for the job.
Makes sense. And this all ties back to that historical shift we talked about, how we went from encoder-based models dominating to now where it's almost all decoder-only models.
Right. We talked about how that was driven by the focus shifting to text generation and things like that. But this research suggests there might be more to the story. Like, maybe the choice of architecture isn't just about what you want the model to do, but also how efficiently it can do it and what kind of reasoning it can handle.
So decoder-only models might be great at generating text, but encoder-only models might be the champs when it comes to complex reasoning.
It's possible, and that's why research like this is so important. It helps us understand the strengths and weaknesses of different approaches so we can choose the right tool for the job.
I like that. A toolbox full of different LLMs, each with their own specialties.
Exactly. And this paper is like adding a new tool to that toolbox and giving us the instruction manual for how to use it.
Awesome. So we've talked about the autoregressive communication model, that indistinguishable decomposition technique, the difference between encoder-only and decoder-only models. That's a lot of ground covered.
It is, and it all points to the same thing. We're starting to get a much deeper understanding of how these multi-layer transformers work, where they excel, and where they need a little help.
So we've spent a lot of time digging into these limitations. Like, it sounds kind of doom and gloom, Transformers can't do this, they struggle with that.
Yeah, but I think it's important to remember that this field is moving so fast. Like, what seems like a limitation today might be solved tomorrow with some new architecture, some clever training trick, who knows?
That's a good point. This research is just a snapshot in time, right?
Yeah.
It's not the final word on what these models can and can't do.
Exactly, and that's what makes it so exciting to be following this field, right? It's constantly changing, always pushing the boundaries.
And honestly, finding those limitations, that's how we learn,
Yep.
how we make things better.
Absolutely. It's like every time we hit a wall, it just makes us more determined to figure out a way around it, or even just break right through it.
I love that. And it's not like these limitations mean LLMs are useless or anything. We're already seeing them do amazing things.
Right. And this research is about understanding how they work at a deeper level, so we can use them even more effectively, build even more powerful tools.
So it's not about being discouraged by the limitations. It's about seeing them as opportunities for growth, for innovation.
Perfectly put. And who knows, maybe someday we'll look back at this paper and be like, remember when we thought LLMs couldn't do that?
I can't wait for that day. But for now, this paper It's given us so much to think about, so many new insights into how these models work.
It really has. It's like a peek behind the curtain, you know? And
Yep.
I'm sure it's going to spark a ton of new research, lead to even more amazing discoveries.
Absolutely. And on that note, I think it's time to wrap things up. We've covered a ton of ground today, explored some really complex concepts.
Yeah, we went deep, but hopefully it was all clear, made sense.
I think so. And as always, we'll be sure to link the full research paper in the episode notes so everyone can check it out for themselves.
Definitely do that. And, keep those questions coming. This field is moving so fast. There's always something new to learn, something new to discuss.
Exactly. So until next time, keep exploring, keep experimenting, and keep that curiosity burning.
And most importantly, keep learning. The world of LLMs is full of surprises, and the future is, well, it's full of potential.
Couldn't have said it better myself. Until next time, everyone.